Hi, in this lesson I want us to look at earthquake epicentres and how we as geologists can locate the epicentre of an earthquake after it's happened. It's an important part of understanding patterns of earthquakes, to see if changes are happening, and to be able to predict future hazardous events. For this lesson, you're going to need a ruler, some coloured pencils, a compass if you have one, but you can manage without, and a calculator. You should also have a scan of the map from the atlas of the part of the world that we're going to be looking at. Okay, let's go. This is an earthquake hazard map of the lower 48 states of the USA. The different colours represent the level of risk. The brighter the colours, the higher the level of risk. So you can see here, as we'd expect, quite a high level of risk running down the west coast of America through California and Oregon. This is the location of the San Andreas Fault. The red blob in the middle, on the boundary of sort of Kentucky, Tennessee, Arkansas, Missouri, is a very odd, very enigmatic area called the New Madrid Fault Zone. It's quite complex, the geology of that area. I don't want to really get into that in this lesson, okay? But don't be afraid to go and look it up. On this map, you can see the black triangles scattered across the US. These areas are the National Seismic Network. This is the places, or these are the places, where the United States Geological Survey monitor earthquake activity across the US. I want us to look at some of the results from a few of these stations to show how we go about locating earthquake epicentres. Okay, we're working on pages 6 and 7 of our booklet. The first thing we need to do is we need to understand how two types of earthquake waves, what we call P waves and S waves, travel. They move at different speeds. So if we plot a distance time graph for these two earthquake waves, it'll show us how far each of these waves will travel in a particular time. Now you can see in your booklets that P waves travel at 5.6 kilometers per second. S waves are slower at 3.25 kilometers a second. So we can actually plot a graph to show how these move. We could, for example, look at how far they'd have gone after 1 minute and 2 minutes. Plot those points on our graph, join them up from 0, and we have a straight line that represents the movement of a P wave. We do the same for an S wave, and we should have a graph then with 2 lines on it. Okay, give that a go now and plot those lines on your graph. Okay, let's have a look at what you've come up with. This is my line for the P wave. You can see after 2 minutes, the P wave has travelled nearly 700 kilometres. The S wave, travelling more slowly, after 2 minutes, has travelled about 380 kilometres. So we've got these two lines. We're going to come back to those in a moment. Part B of question 3 looks at where these earthquake monitoring stations are located. Now for this, you'll need a PDF copy of the page in the atlas that I've sent you. There are 3 earthquake stations that we're going to be looking at. First of these is in Utah, in a place called Cedar City. The second is in the outskirts of Los Angeles, a place called Pasadena. And the final one is in a place in Nevada called Tonopah. You've got 3 diamonds shown on your map. Those are the locations of the seismic stations. Label them up. Which one's which? Have a go at that now. Okay. We should now have these 3 stations labelled up. So we've got Pasadena there in Southern California, Tonopah in Nevada, and Cedar City in Utah. I've used different colours here to help me differentiate between the results from each of them. You might want to do the same. Okay, so we now have our 2 key pieces of information really to be able to start working out where the epicentre of an earthquake actually is. If we look at your earthquake graph, you'll see that there's a gap between these 2 waves. So at any particular place, there's going to be a difference in time between P waves getting there and S waves getting there. It's this gap that tells us how far those waves have travelled from wherever the epicentre is to the station we detect them. Now to do this, or to work this out, we need the seismographs. These are the records made when the earthquake reaches a seismic station, it shakes the ground, and that shaking is recorded on these graphs. We can see the gap between the P waves and S waves on these graphs with this time gap that I've highlighted in pink there. The P wave is the first one to arrive. You can see it's not very big. Sometime later the S wave shows up, causes more shaking, but that gap in time we can measure. You'll see there's a horizontal scale on that seismograph. And once we've worked out what that time is, we can take that time and find where that time gap will be on our graph, and we can then read down to the bottom of that graph to find out how far that wave has travelled. Once we've done that, we can go to our map and we can then plot a circle around the seismic station that has the same radius as that distance, because that's how far we know the earthquake has travelled. If we do 3 circles, where those circles meet, that's our epicentre. So, what I want you to do now is press pause and have a go at question part C. Once you've completed that, have a go at parts D, E and F. Okay, E and F, of course, are the digging deeper. That's optional if you want to give it a go. Have a go at that now, see what you can come up with.